In this chapter, we are going to learn simple linear regression, association between two continuous variables. The word simple linear regression versus multiple linear regression, and we use a simple linear regression for linear regression where the independent variable is only one continuous variable and there is no other independent variable in the model. Whereas multiple linear regression, and we use when we have more than one independent variables. Independent variable can be continuous or categorical. Okay. So this is today's example. And here we have data on body weight and plasma volume from 8 patients. Okay. And mean of the body weight in kilogram is 66.87 and mean of plasma volume is 3.0. Okay. And when you have two continuous variables, typical type of graph you expect is scatter plots. So you plot y, value of y, value of x, and each data point correspond each patient. Okay. And then you draw a straight line, and so that residuals, which is straight down distance between observed value to regression slope, is minimized. Okay, so you, especially when you take a summation of these residuals, okay, and you draw a line, or computer draws a line, where the total sum of these residuals are minimized. Okay, and that's defined linear regression. Right? So let's repeat. What is the term residuals? Residual. We sometimes call it error, and that is a measurement error or residuals, which is the distance between each observations to regression line. It's a straight down distance, straight down or up. Okay, and this straight line is defined by two elements. One is intercept and one is slope. So if you know two numbers, you can define this linear line. And these are the values, straight up or down from observed value, which is lining on the regression line. And this is called predicted values. Okay? So using this regression, and you can predict the value of plasma volume for future patients. And those would be the value, okay, and which is sitting on this regression line. Let's look at this graph. And this is a graph, and I draw a line where y stay at the mean value. Okay. So when you see the line where the slope is 0, it's perfectly flat, and this means body weight does not add anything to predict the plasma volume. So wherever body weight is, it predicts just a mean value of a plasma volume. Okay. So when you look at the residual, in this case, if you sum these residuals up, and you will see these distances are much larger than the distance you find in this line. Okay, so I hope now I convinced that this line is drawn where the residuals are the minimum, smallest. Okay. All right. Let's go back to look at this regression line. Okay, so now let's think what slope of 0.04 really means. And let's see if you can explain it using a general terminology. Then what is 0.09, which I already said is intercept. Let's explain this intercept using general terminology. So slope, okay, in this case is beta, is increase in y, that's this much increase in y, where x increase 1 unit. Okay, and that's how we explain beta. So the beta indicate, beta in this case 0.04, there is a 0.04 liter increase in plasma volume by 1 kilogram increase in body weight. Okay? And how about intercept? Intercept is a value, expected value of plasma volume for a person whose body weight is 0. Okay? So that is 0.09. And of course, there is no person whose body weight is 0. So intercept is actually, we call it nuisance parameter. It's not really meaningful. Okay? And especially when we want to look at association between y and x, and we don't really care where the alpha is lying, and we care if the slope is flat or slope is not flat. Okay, so here is a quiz. Does intercept alpha or slope beta change when you change a unit of independent variable? Quiz 2. Does intercept alpha or slope beta change when you change a unit of dependent variable? And I want you to make a guess. And let's look at in actual analysis. Okay. So here we are going to create a weight variable, and now we make unit being 10 kilogram instead of 1 kilogram. So how can we do that? We divide weight by 10, right? Okay, and so let's use this variable in the analysis. So for linear regression, we use regression and linear. Okay, and the plasma volume is dependent and weight 10 instead of weight is independent variable, and see what happened. And intercept value does not change. It was 0.09. Actually, I rounded up, so it was 0.086. And before we change unit of weight, and then the beta coefficient slope for weight changed from 0.0436 to 0.043. It changed from 0.0436 to 0.436. So beta coefficient is multiplied by 10. And does it make sense? So now we say there is 0.436 liter increase in y by 10 kilogram increase in body weight. And let's see what happened if we change dependent variables unit. So we create new variable, plasma milliliter. And how can we change plasma liter to milliliter? We multiply by 1,000. Okay, and we go to do regression linear. Right. Instead of using plasma, we use plasma milliliter, and then let's put the original weight variable back and see what happened. And changing unit for dependent variable change both intercept and body weight. And the good news here is, even though changing unit change intercept and body weight, it didn't change p-value. So p-value stayed 0.029 in all three analyses. Right? So if the changing unit, whatever unit you choose, only impact on beta coefficient, should we worry or shouldn't we? And this is actually from a table, and I was asked to review a manuscript today. So this table was in the manuscript, and I found this odd-looking table, right? So what we did is we did a linear regression, and the dependent variable is F2 isoprostine, and by 2 markers. And I can't tell you what the biomarkers, because we haven't published this work yet, but let's say marker A and marker B. And marker B, p-value is very significant, but beta coefficient is very close to 0. I heard many people say there is not much effect because beta coefficient is close to 0, although p-value is significant. And what does it mean? Why you have too many zeros in beta coefficient? Because unit is just one unit in these markers. And let's see this, if this marker range from 0 to 10,000, and I'm sure the impact made by 1 unit change in this marker is trivial, right? So we need to avoid using a unit which doesn't really have any clinical meaning, right? And my suggestions for these, the authors, is why don't we change unit for this independent variable from 1 to 1,000? Then we can move this decimal in 3 places, so we can get rid of 3 zeros. Okay. So here is a recommendation from Annals of Internal Medicine. Okay, let's read it together. Don't give readers an estimate such as an odds ratio or relative risk for a 1 unit change in the factor of interest when a 1 unit change lacks clinical meaning. For example, 1 year in age or millimeter of mercury of blood pressure, or any other continuous or interval measurements with small unit. All estimates should reflect a clinically meaningful change along with 95% confidence bounds. Okay? So, based on this recommendation, and my recommendation also agreed, and let's, from now on, let's try to use a unit for your independent variable which reflect the clinical significance, clinical meaning to it. So next, I like to make comparison between linear regression and a Pearson correlation coefficient. So when you conduct a linear regression, we talk about intercept, we talked about slope. And another metrics linear regression gives you is called R-square. R-square in this case is 0.58. Okay? And this means 58% of variation in Y plasma volume is explained by body weight. So higher the R-square is better, and it can go up to 100%. Right? So let's look what this R-square is computed, how the R-square is computed. So R-squared, as I say, it's the amount of variation in Y which is explained by X. And this is how Spss is computed. First, you fit the linear regression line, then compute sum of residuals, which is distance from observed value to mean value. Okay, so that's 3 is a mean of plasma volume. Okay, that is the total variation existing in Y. Okay. Then we compute distance from this mean to regression line and sum it up. Okay, that is explained. That we can say variation explained by the model. The model means by body weight. Okay, and then you take a ratio, red divided by blue, and that is R square. Okay, so if the regression line perfectly explains plasma volume, then this red actually part would be the same as blue, so R square would become 100%. Okay, and then when you square this R square, okay, and that actually match with Pearson correlation coefficient. And the p-value you get from Pearson correlation coefficient or p-value you get from linear regression is the same. It's mathematically the same thing. Okay? So when you have two continuous variables, you have a choice whether you use Pearson or linear regression, simple linear regression. And you don't have to worry too much because p-value will be the same anyway. Let's review what is the Pearson correlation coefficient. Based on the result of linear regression analysis, which gave R square of 0.03, that's 3% of variation in Y is explained by X. And let's compute Pearson correlation coefficient. I use a value R for this. Okay, what is R? R is square root of 0.03, which is 0.17. Okay, so that's the R. Then let's compute Pearson based on this. So Pearson would be square root of 0.04, which is 0.2. Okay, so there is correlation of 17.17 versus 0.20. So it's actually this one is minus, this one is plus. Then correlation wise it's similar. Let's look at the beta coefficient. Okay. And beta coefficient is 0.74 and this one is 0.07, which is a lot difference. This one is 10 times larger than this one. Okay, so here I want you to think what this means. Does this show 0.74 indicate stronger association than 0.07? And the answer is no, because as I said, these parameters units are all up to what is 1 unit. So in the D-dimer range from 0 to 6,000 or even higher, maybe 7,000. Okay, then change in D-dimer by 1 unit is very tiny, and compared to change in NSE, that's another biomarker, and here. Okay, so one this is 4, so one measure is about this much. This is 1, so it's amount of Y increasing when X increase 1. Okay, so slope indicate this length. But here 1 is so tiny, so I can't even draw it. It's just too tiny. One unit is probably like that. Okay, so it's not really fair comparison to compare value of beta, two beta slopes. Although the correlation coefficient it was 0.17 versus 0.2, so you are okay to directly compare correlation coefficient. Why is that? Correlation coefficient is a standardized beta coefficient. So how standardization is done? Okay? So standardization is done by standard deviation in both Y and X. The Y variable in this example is mean t-score. It's a cognitive score for the patient measured 3 months after the patient who discharged from ICU. And these two markers are the related markers at the ICU admission. Okay, so in order to be able to compare these two numbers, we have to standardize x-axis, right? The length of x-axis. So how do we standardize? So here we use the standard deviation. So if the data is normally distributed, what can we say? About 75% of data fall within the range of plus minus 2 standard deviation. Right? Okay? So same as y. If the y variable is normally distributed, it's about 2 standard deviation in the range within 2 plus minus standard deviation range. 95% data exist. Okay, so 0.17 is a slope where the unit is a standard deviation of y and standard deviation of x. Right, so the 0.17 means there's 0.17 standard deviation of y increase by changing x by 1 standard deviation of x. So that's how you interpret the result of a correlation coefficient. So it is standardized, and therefore you can directly compare these two values to show the magnitude of association. Okay. All right. So let's talk about two main goals of linear regressions. One is testing association. So we want to test whether the variable A and variable B, or variable X and variable Y, has association. Okay, so we have a scatter plots, and then if we see the line like that, the steeper the line, higher the beta, it shows higher the association, right? Okay, so for associations, we use beta, and we don't really care what is the intercept value. Okay, and another use of linear regression is for predictions. So let's say you collected data from 10 patients, and then that's 10 patients you use to draw this linear regression. Okay, and then you want to use this regression line to predict person who come in the future. Let's say after you finish this study, and then you saw this new patient, and then his body weight is 60 kilogram. Okay, 60. So what you do is you plug the 60 in this regression line, and then calculate the value of y, okay, based on the regression line. So that is 0.04, 0.09 plus 0.04 times 60. So that will give you estimated plasma volume for this new patient whose body weight is 60. Okay? So as you may have realized, prediction analysis involves intercept as well. The association analysis, we only look at beta, but prediction, we do look at intercept. And then both intercept and beta coefficient has some degree of uncertainty. So therefore, the predicted value has higher degree of uncertainty than the uncertainty in existing in beta itself. So therefore, usually prediction model require larger amount of sample size to overcome those added variations by using intercept. Alright, we are going to do SPSS demonstration of simple linear regression. So in the Dropbox, and you can find bodyweight.sav. So that's the data set we're going to use today. Okay, then we do open. Right. So we use plasma as dependent variable and weight as independent variable. So let's do linear regression. Okay, and let's do graph first. I want to see data first. So to do scatter plots, and you drag this, put it into this box, okay. And then you choose. See what happens. Yeah, we drag this, okay, and then put the plasma and weight. Okay, if you want to draw a line, you can do that. So the line you can draw by double clicking and put the straight line. Okay, so that's the line. And this line is strange because I think we're forced to go through this line is wrong because we forced the line to go through the 0, 0 coordinate. So we don't want that. So this is a regression line. And then this does not have a formula. We don't know what is the intercept, which you extrapolate it, and where this line merge with y-axis, that's the intercept. And we don't know intercept, we don't know slope, so we have to perform linear regression. So linear regression, actually we eventually start using GLM, but today, and there is a reason I have to use other method. It's here, through regression, and then you do linear. So this will do linear regression. Okay, and then put the plasma as dependent and weight as independent variable, and click OK. So here is a formula. Okay, in R square, not formula, here are the result. R square is 0.567. If you take a square root of that, you get 0.759, and which is actually exactly the same as Pearson. So let me do the Pearson correlation coefficient. Coordinate by evaluate by evaluate. Okay. And if you do Pearson, correlation coefficient is 0.759, which is exactly the same as the number you computed here. Okay, and then you look at p-value for regression. So this is a p-value for the slope. The same thing you see, this is a p-value for the slope. Okay, so this is a slope, and constant means intercept. So this is the intercept value. Okay. So based on this, and then here is our interpretation. Both plasma volume is estimated to increase by 0.044 liter by 1 kilogram increase in body weight, and the association was statistically significant with a p-value equal 0.029. Okay, and you could put the confidence interval to this p-value, and to do that you go back to linear regression and then click on option, and there is options for confidence interval. See, yes, here. Okay, you click confidence interval and continue and OK. Okay, so how do we interpret this confidence interval? And we see that if the null value, in this case is 0, is included in this range of confidence interval, and then that will link to p-value larger than 0.05. So in this case, p-value is less than 0.05, so therefore 95% confidence interval excluded 0. Yeah, that makes sense. Okay, so let's go next. So next slide. Okay. So next slide, I will show you how to put the confidence interval in this regression slope. So go back to SPSS and go to output file where we already did the scalar plots. Okay, double click, and there is an icon. Let's see. Okay, and then you click, and so what I did is I clicked on anywhere on the regression line. Okay, and then go to fit line. So if you need properties box, then you click on fit line, and then here is the options we can do confidence interval. So I want confidence interval. When you click means you draw confidence interval around regression line. Okay, so that will look like that. If you click individual, this is what happens. So mean is a confidence interval for beta, and if you click individual, this is a confidence interval for your predictions, predicted value you're trying to make. So prediction involves the value of alpha, which has more variations. So confidence interval becomes much larger. And usually when you want to show that there is association between x and y, and then put the confidence interval for that, and click on mean confidence interval. Okay, so that will give you confidence interval for the beta, which we need for association analysis.